All right. Yesterday, all we did was talk about a specific probability model called the geometric model that's based on Bernoulli trials. You need to get in the habit of checking before every question that you have Bernoulli trials. If you don't have Bernoulli trials, then you can't use a geometric model or the one we're talking about today. Okay? There are Bernoulli trials. There's 2 outcomes only, and the events or the trials are independent. All right. So for the geometric model, you had P probability of success. We're actually talking about a random variable, the number of trials until the first success occurs. Because this is a probability model. It's just not a table model like we did in chapter 16. It is a probability model. If I ask you to find the probability that you get you roll the first 5 on a die on your 6th roll, then I'm asking for the probability that you get your first one on the 6th. And you could find that probability. That means you didn't get a 5 the first 5 times, and you got a 5 the last time. You could do that probability before in chapter 14, but we're actually talking about a probability model here. It's a little bit different. So because of that, we have expected value, our mean, is 1 over P. You have to know that. It's not written down anywhere. And you are expected to know that if it asks about an expected value, here you're asked about the first something happens, you should know it's 1 over P. The standard deviation is a square root of Q over P squared. They hardly ever, if ever, ask about the standard deviation of a geometric model. It just doesn't come up very often. They'll ask you about the other model all the time, but not this one. So I'm not going to worry about it as much. Okay? But you have to know the expected how many free throws miss. I was talking about geometry, my first something. Okay? So it's important to note, geometric model talks about the first something. Always. First. That's the key word. All right? So, some other examples that we didn't get to yesterday that talk about geometric model. We're talking about a customer service call center of a major credit card bank. And it says, cardholders call for a variety of reasons, but regardless of the reason for calling, if they hold a platinum card, Raj is instructed to offer them a double miles promotion. So if they have a platinum card, then he has to offer them the promotion. About 10% of all cardholders hold platinum cards, and about 50% of those will take the double miles promotion. On average, how many calls will Raj have to take before finding the first cardholder to take the double miles promotion? How do I know this is a geometric model that I'm using? Yeah, it says before finding the first cardholder. That is indicating we're using the geometric model. If it says on average, then what am I finding? The mean, which is also known as the expected value. So we're looking for the mean or the expected value. And how do you find that for the geometric model? 1 over P. Now in this case, our probability of success, P, would be the people that take the double miles promotion. Yesterday they just gave, we got a little more information to figure it out. It says 10% of cardholders hold platinum cards and 30%. So how do I find the probability that people that have platinum cards that take the promotion? Right, so P is 0.1 times 0.5. Because you're talking about the question about all cardholders, and only 10% have a platinum card, and you're not getting this promotion unless you have a platinum card. So you're just using the multiplication rule from chapter 14. If you don't have a platinum card. Yeah. Okay. So what's 0.1 times 0.5? 0.5. So we have 1 over 0.05, which is what? What? Oh my gosh. 20? Or 1.000, something like someone over here said. 20. So Raj would expect to take 20 calls before the first person accepted this offer. That's what that 20 means. I don't take the time to write these things out in context when I'm teaching, but I normally try to say them out loud. So that 20, if you're interpreting it, means you have to expect to take 20 calls before the first person takes the promotion. Questions about protein? Not so bad, right? I was at 15. Only 4% of people have type AB blood. So first, before we do any of these questions, we have Bernoulli trials. What do you have to have in a Bernoulli trial? 2 outcomes. So I have 2 outcomes. Yes, we have 4 sources of the AB people. So we can have AB or not. And then what about independence? Sure, are we going to see enough people that would change probability? No, we're not going to sample more than 10% of the population of people. Never going to. So less than 10% of the population, and so we have independence. So that means that I can use the geometric model or the model we're talking about tonight. Otherwise, it doesn't. Right. On average, how many donors must be checked to find someone with type AB blood? Why is this geometric? Yeah, that's we check to find someone. That's the same thing as saying to find me first someone. Right? But that's AB blood. So what does that ask me to find to find the expected value, which is 1 over P, which in this case 1 over P is 1 over 0.04, which is 25. So we would expect to see 25 donors before we saw the first person that had AB blood. Does that make sense? Okay. On part B, what's the probability that there's a type AB donor among the first 5 people checked? Right, so it's saying first, so there is a type of among the first 5 people. So we're looking for one person, like the first one, among the 5. So that could be, I'll write it all out. That would be, you found it the first time, right? Or you found it the second time, right? Or the third time, the third person, or the 4th person, or the 5th person, right? So this is the first 5, I would stop, but I have to add all of this together. So this would be a good transition to how to do some things in your calculator. Yeah. Okay, so in your calculator, there are 2 separate geometric model functions, right? You need to go to second distribution to the distribution menu. This is becoming going to become more and more and more important. You're going to use this menu all the time, second semester. Now it says on your note sheet to get to them, instead of taking as much time as you would just scroll down, they're the last 2 in the menu, so just scroll up. And there they are, they're E and F. You have Geomet PDF and Geomet CDF. Okay? You're going to use both of these. You know how on normal functions we don't use PDF? We only use CDF? Well, we're going to use PDF and CDF pretty much for everything we do in the class for the rest of the year. So you have to know the difference between the 2. Okay? Geometric model, PDF. PDF stands for probability density function. So for a geometric model, we're looking for the first something to happen. You would use PDF if you knew the exact specific probability you wanted. Like I want to know the probability that I get my first free throw on my 6th attempt. Not in the first 6, but on the 6th attempt. So
So it's very specific. You use PDF. CDF stands for cumulative density function. So cumulative should be your clue. Cumulative adds stuff together. So you'll use CDF if I want to know the probability of my first free throw in the first 6 attempts. Alright? So PDF is for a specific, like one thing. CDF is for when you're adding stuff together like we are in this problem right here. Right? Yeah.
Alright, so let's do number 15b. That's on the screen. So probably that there is a type AB donor among the first 5 people checked. So I want to know probably the first one in 5, not on the 5th person, but in 5. So we're going to use CDF, not PDF. It's on your note sheet. All right, so you get the same menu for both of them. So you won't be able to decide which one you're using just by the menu.
If you go back and look at PDF, they're the same menu. So the menu will not help you. It'll be your responsibility to know which one to use.
So we are using CDF because we're trying to find the first in a certain amount, not just the first on a specific one. P is your probability of success. So in this case, the probability of getting a type AB person. So what's that probability? 0.04. And your X value is the number
of trials, or in this case, the number of people that you're checking. So I'm checking 5 people, so X is 5.
So you should get 0.1846. Now,
just for argument's sake, I'm going to type in all the stuff that I wrote a second ago. Okay? Here it is. You get 0.1846. So I'll save myself time sitting here in it. You got 1.1846, which is all of the stuff I wrote in green. So it gives you the same thing. This is much quicker. What do you agree?
on part C, it asks almost an identical question. It says, what's the probability that the first type AB donor will be found among the first 6 people? Well, it's the same question. We just have 6 people instead of 5 people, right?
We do the same thing. CDF. The word there was asking the same thing. And so we changed 6.
You get 0.217. Good question. On a test, especially the AP exam, you should never write a calculator function down. They'll ignore it. They'll be like, okay, I don't care. So don't use your calculator function. So in this case, what you would want to do if you're going to use your calculator,
you want to, for these two we're talking about, you want to define that you're using a geometric model. So there's a notation. So you would write geom 0.04. That says using a geometric model with a probability of success of 0.04. Alright? You'd probably want to check the Bernoulli trials that I wrote in red over there. And then you could find the probability. You could write it out if you wanted to, if it wasn't long. And then do it in your calculator, or you could just find the probability and it'll be fine. Okay? Yeah, and you could say for this question, yeah, equals. I'd be okay with that. A lot of the time on the AP exam, geometric probabilities come up in multiple choice, not the free response. Binomial, we're doing today, comes up on the free response. And there's much more stuff you would write down, so I think it'll look not just doing something. You could just write it out to show where, and then put in the calculator for the answer. But like the one on the homework, which I'm going to do in a second, it asks for the first 10 chips. Okay, so, everyone gets it hard? Let me finish this question. The last one is hard, but I want you to think about it. It says, what's the probability that we won't find a type AB donor before the 10th person? Right,
done that question, maybe not last night because we didn't have the calculator, but you could have figured them out. You would have had to write it all out. But who wants to do that?
Wait, let's go back to the one. Let's talk through real fast. The one from the homework 10B. It's all up here, but we can hear real fast. It was asking about the defective parts. And it says, what's the probability
that you find the first defective one in the first 10 parts of first chips?
10 chips.
So if you're using your calculator,
or using CDF, PDF, our probability of being defective was 0.02. Now we're doing 10 chips. So 0.1829, which is what you would have gotten if you did it all out by hand. I know. Alright, question so far. Alright, we're probably not going to use our calculator too much more today. I won't get to show you the next model on the calculator. It's not going to. Alright. Now.
keep in mind, geometric models only used for what? Probability of the first 6 steps. First. So, I'm going to go through these questions. We're not answering them. I'm going to go through these questions, and you're going to tell me which ones of these you could have done last night, because you couldn't have done all of them. Okay, you're going to tell me which parts of the question you could have done with the geometric model. Okay? Sound like a plan? We haven't learned the other model yet. I'm just making sure you can keep them separate. So before I even teach the other one, we're going to make sure you got this one. Alright, so assume that 13% of people are left-handed. If we select 5 people at random, find the probability of each outcome described below. So part A, the first lefty is the 5th person chosen.
Yes, if you're doing it on the calculator, what do you see? Or PDF?
PDF, the first one is the 5th, not in the first 5. So PDF gives you a specific one. Okay. On B, there are some lefties among the 5 people. You couldn't
do that last time. That's the first thing.
So generally, geometric model, there's only one of what we're looking for, right? All right, C. The first lefty is the second or third person.
You would do PDF and add them together. You would do first and 2, first and 3, and that here.
CDF won't do that. You can't define boundaries of which ones you want it to do. On D, there are exactly 3 lefties in the group.
Nothing is the first thing, so we can't.
E, there are at least 3 lefties in the group. And F, there are no more than 3 lefties in the group.
So geometric says specifically the first of something. So there's like one of them. There aren't multiple. Okay? On 19.
Same 5 people. How many lefties do you expect? No. For geometric, it's how many lefties until the first one.
No. Geometric is
How many until the first one, right? Not how many lefties. So then you can't do B because that goes with A. And so C says if we keep picking people until we find a lefty, how long do you expect it to take?
you could answer that question, right? That was one of you want to look at. Alright, so far so good. Geometric, you can only use this is the first of something, and there's one of them in the group. You're the first one in the group. I keep making this a big deal because for whatever reason last year we did not keep that straight. We're not making this mistake this year. First thing. Yes?
Okay, then let's talk about the binomial model. If you have Bernoulli trials, you can use a binomial model to answer other probability questions. So, for example, cereal boxes, right? We got to keep going with the stupid cereal boxes. I know. Let's say you have 5 boxes of cereal, and you want to know the probability that you get exactly 2 out of the 5. That's when you would use the binomial model. The binomial model is asking for the number of successes in a specific number of trials. So I want to make exactly 7 free throws out of my 15. I want to make exactly 10, I want to get exactly 10 heads when I flip the coin 20 times. All right, so it's an exact number of successes out of a specific number of trials. Does that make sense? All right. So the binomial model, you have a number of trials in, you didn't have in the last one, we just had P. And we still have probability of success, P. So the geometric model N was not there, we just had P. So you know how we say geometric model, like we say G, P, and you would put the probability of success there? If we're talking about the binomial model, you do binom N comma P. So far we have 3 models that you should be able to define. The normal model, mu comma sigma. You have the geometric model, and now you have the model. You should know that notation. We haven't done anything with the binomial model yet, but that's the notation for it. All right? Now, let's say I want to know there are exactly 2 Tiger Woods cards in my 5 boxes of cereal. How do you think you're going to find that? The probability of getting a Tiger Woods card is 0.2. How do you think you would find that? You want 2 out of the 5. Well, if 2 are Tiger Woods cards, that's 0.2 squared, right? And then 3 are not, that's 0.8 to the third, right? And that's going to be part of how you do this. The problem is you're talking about 5 cereal boxes, and you're talking about the same probability, but the order is going to matter. So here's the Tiger Woods example. If you did 0.2 squared times 0.8 to the third, like I just said, that's the probability of finding Tiger in the first 2 boxes and not in the next 3 in that order. But you could find Tiger in the 3rd and the 5th boxes and still have 2 successes. So in doing all this, the order matters. You're not going to have to write all this out. What mathematical function can you use that helps you figure out all the different things that could happen? Combinations. Remember those combinations from algebra 2? Combinations. We're not doing permutations, and we're not really doing combinations, just part of the formula. I need to find the number of combinations where Tiger Woods is in 2 of the boxes and he's not in 3 of them before I can multiply it by this probability. Because that could happen that many times. All of those are going to be disjoint events, so that's why you're just going to multiply, because you can do that. But so you end up with this combination formula. You solve this in algebra 2. It's N choose K. N is the number of trials, and K is the number of successes. Your calculator will do it for you, so you don't have to do all that. Okay? So for the Tiger Woods example, there's 5 trials, 5 boxes. You want 2 Tiger Woods cards. So there's 10 different combinations, and so you did 10 times that probability we talked about. Now, in general, for the binomial model, here is the equation. That looks all complicated, but it's not. I want how many trials, that's N, how many successes I want to make 3 free throws out of 7. I want to make 10 heads flips out of 22, whatever. The probability, P is probably the success to the whatever power, how many we want. And then Q is just the complement to whatever's left over. I wouldn't even make a big deal about this. Last year, I didn't teach my AP students about this formula. The only reason I make a point to do it, because you can do all this in your calculator. The only reason I make a point to do it is because on the AP exam, on the multiple choice, inevitably, there is a question about the binomial model, and it gives you all the information, and then it gives you all these possibilities of how you would find probability, not actual probabilities, just like the formulas. And you have to know that this is the binomial model so that you can identify which one it is. It's on the AP formula sheet, that formula. I know, but they're making sure you realize it's binomial when you read the prompt. So, you don't have to memorize that formula. It's on here. We won't hardly use it at all in class, but you need to be aware of it. Okay? So today when I'm doing that, I'm going to do one by hand, and I'll probably maybe show you one with a calculator if I get a chance. All right, so in summary, the binomial model, you probably have most of this written down already. You have a number of trials N, the probability of success P, your random variable is the number of successes in a certain number of trials, and you have this crazy formula that you don't have to write down if you don't want to. Important though, it's a probability model, so it's going to have an expected value and a standard deviation, right? If I want to know the number of heads I expect to get out of 10, it makes sense to take the probability and multiply it by the number of trials. That one should be obvious. I should be like, oh, I get how they get that. What may not be as obvious is how they do the standard deviation, which is the square root of n times p times q. All of this stuff is on the formula sheet. The only thing that is different is that, like I said yesterday, the AP people, Q is not a standard notation. So they're going to write Q as 1 minus P. That's what it is. But all of that, there's a whole section. If X has a binomial distribution with parameters n and P, then it gives you the probability formula, it gives you the mean, and it gives you the standard deviation. All right there. Okay? Yeah? Let's go back to those lefties questions, and let's actually answer some of them. Okay? All right, we're not going to do A and C, because we could have done those yesterday, and I'm trying to focus on the binomial model. So we're going to do B, D, maybe a few more if we have time. I'm going to start with D, though, because it's the most easy example. Most easy. Is that how you say that? I don't know. Easiest? Whatever. What's the probability there are exactly 3 lefties in the group of 5? That is the perfect example of the binomial model, right? We want exactly this many out of this many. So I'm going to write it all down in the formula first. And then I bet you can guess how to do it in the calculator just by knowing how to do the geometric ones. But I'll show you by hand first. So I have 5 trials. I want 3 lefties. What's the probability of getting a lefty? 0.13, so I want 3 of those. So what's the probability of not being a lefty? 0.87, and there's 2 of those. So in your calculator, if you're going to do combinations in your calculator, you type in the top number first, 5, go to math, scroll over to probability, number 3 is combinations. So you would do 3, so there's 10 combinations, and you multiply by the probability you're trying to achieve. And we get 0.0166, right? Now, you don't have the sheet in front of you because I don't have too much time to talk about it today. But you know how we were just in the distribution menu with geometric PDF and geometric CDF? Well, there's also it's in the very middle, so you can scroll up or down. There's a binomial PDF and CDF. If we're doing exactly 3 out of a group of 5, do you think I'm going to do PDF or CDF? PDF, doing an exact situation. And if you look at it, it asks for the number of trials, 5. The probability of success, in this case wanting a lefty, 0.13. I use how many lefties I want. It's 3. And then you hit paste. It gets you the same. Yes. So, those are available to you. Again, I need you to understand the formula exists, because if not, you won't be able to answer some multiple choice questions sometime that should be easy to answer. All right? Let's look at B. There are some lefties. How do we find something when we were doing stuff in chapter 14?
When one minus like some means 1 or 2 or 3 or 4 or you do 1 minus, well, you have 1 crazy. I have no lefties. It's just 1 minus 0.87 to the fifth. Feeling that they pull on formula equation, but 5 choose 0 is 1, 8.13 to the 0 power is also 1, 0.87 to the fifth. Oh my god. So that answer.
Does that make sense? Yeah, so far so good. We're going to come back to E and F tomorrow. So I want to make sure I have time to explain. You could try them. I'm not saying that they're difficult, but I'm just going to take time to explain.
Look at number 19. Rapid understanding.
How many lefties do you expect? Well, this is Bernoulli trials. We're using a binomial model. So how do we figure out how many lefties we expect?
It's n times b, which is the number of probably you're lefty. Right. So 5 people times the probability you're lefty. 0.65. That should make sense. But in an absolute standard deviation, the standard deviation is the square root of n times p times q. That's square root of 5 times 0.13 times 0.87. That's 0.7.
Yes, maybe, possibly, could be. All right.